Welcome to another informative video on electric motor classification. In today's videos, we will be looking at stepper motors in general. The part that made up these motors will be looked at, and their applications. So let's get started. Stepper motor is commonly found in robotic machines and some special equipment. Unlike the other type of DC motor we know, these motor is more precise and it deliver a great deal of torque when compared with other motors of the same ratings.
Stepper motors, due to their high pole count, offer precision drive control for motion control applications. They have a high torque at low speeds, and they're also relatively inexpensive and widely available.
Also, stepper motors are known to push harder from rest. DC motors, on the other hand, tends to have more sustained output. DC motor cannot control the position of the rotor, while a stepper motor has the ability to control the position of the rotor. All this is due to their high pole count, which offers precision drive control for motion control applications. They have a high torque at low speeds, and they're also relatively inexpensive and widely available.
With all these, stepper motors can now be classified as a DC synchronous motor. That is because it is powered by a DC source, but it behaves as a synchronous motor. And it is on this basis that stepper motors are divided into three, which are permanent magnetized stepper motor, variable reluctance stepper motor, and hybrid synchronous stepper motor. So basically, by construction, the stepper motor is made of two parts, which are the stator and the rotor. The stator is made up of stacked laminated sheets, and this sheet has some set of coils that are wound around the stator sheets. While the classification earlier is used to differentiate the type of stepper rotor that we have in the market today.
Of course, the rotor construction varied by design. Overall, the stator coil will induce electromagnet on the rotor. The induced electromagnet will now interact with the rotor to generate a mechanical torque.
As the name implies, the wound coils are switched in step from one coil to another. If the switch sequence is done in a proper way, the rotor rotates, and it is on this basis that the name stepper motor was coined. That is because the rotor rotates in step when the coils switch.
Perfect, guys. Now let's look at the permanent magnetized stepper motor. The rotor of this motor is made up of permanent magnets, and is axially magnetized. This means that the rotor has alternating north and south poles. These poles are parallel to the rotor shaft. The rotor is cylindrical in nature. That is, it will line up and perfectly fit in with the stator of the motor. The stator usually has two windings, and the windings could be center tapped to allow for a unipolar driver circuit where the polarity of the magnetic field is changed by switching a voltage from one end to the other of the winding. Or a bipolar drive of alternating polarity is required to power the windings without the center tap. A pure permanent magnet stepper usually has a large step angle. The step angle is usually at 90 degrees for a two-poles motor. So using these equations, the step angle can be calculated.
Of course, you are right. Looking at the magnet arrange in a typical two-pole settings, the rotor will move 90 degrees across the four pair of the electromagnet shoes. And because the shoes is constructed in a circular forms, hence the reason.
So my friend, this equation is perfect. But the torque delivered will not be strong enough, which is as a result of the time that will be taken before the rotor will reach the next magnetic shoes.
Now, when we add some additional poles, the rotor incremental rotation will now be around 22 degrees. The reason why we now have less axial increment is because of the additional electromagnetic poles. And the poles is now a little bit closer to each other now. And by looking at this calculations, that proved it.
Perfects. More poles will lead to higher torque. This is because we will now have a more magnetic fields that will act on the rotor during its incremental rotation.
Because we now have more electric magnet in a cylindrical form. Less axial rotation will be generated, but it will lead to more torque as a result of the high magnetic torque.
In the coming series, we will be looking at reluctance and hybrid motors. The way this motor works will be looked at in detail and their applications. I hope you have learned something new today. See you at the next one.